Let me show you the output of this program first. Well, you can see here, this is the linear image. And now look at these images. What you can see here is the edges of linear image is being detected here, right? And you can compare these images, then clearly you will find that here we are focusing on the edges of the objects in this image. And objects mean, you can see this is the head, and these are the means first and eyes, and those different features being clearly detected, right? So yes, we are talking about edge detection, and the edge detector we are going to use here is the Sobel and Laplacian. Now let's come back to the class. So today I will first discuss the concepts of image gradient, edge detection, and edge detection using Sobel operator. So you are with Dr. Dibyajyoti Bora. Let's start the class now. So I'll start from the very beginning, right? So our class name is that edge detection in OpenCV using Python Sobel operator. Now, what is image gradient in OpenCV? And anyway, means what do you understand by image gradient? An image gradient can be defined as the directional change in the intensity or color of an image. So directional change in the intensity or color of an image is known as image gradient. The magnitude of the gradient describes the speed at which the image is changing, while the direction of the gradient describes the direction in which the image is changing rapidly. Now, these Sobels and scarce kernels are convolution operators that compute the image gradient. But today's class, we'll discuss about Sobel only. What are the uses of gradient? Now it is clear, na? Magnitude of the gradient describes the speed at which the image is changing, and direction describes the direction in which the image is changing. Now today we are going to discuss about the Sobel particularly, but what are the uses of gradient in image processing? If someone asks, first of all, computing image gradients is a necessary step of many computer vision and image processing routines. Means if we talk about, suppose, object detection in an image, or suppose, say, if I'm giving an example, tumor detection. So in such cases, we take the help of the computation of image gradients. Then gradients are used for edge detection in images, using which contours and outlines of objects in images are found. Gradients are used as inputs for quantifying images for future extraction. Saliency maps which highlight the subjects of an image are constructed using gradients. So these are the uses of gradients. Well, let's come to this point. Theory of edge detection in image processing. How you define an edge in an image. How you define the edge. This is a very particular or famous questions I myself face in many interviews, and you, if you are walking in this area, you may be asked also. So what is edge? An edge in an image is represented by sudden change in the intensity value of the pixels. This change in intensity value can be described by derivatives. The greater is the change in the gradient, the larger is the change in the image. You got it, what is edge, right? Sudden change in the intensity values. Now, we take the help of the derivatives to show this change. In a one-dimensional image, the edge can be represented by a jump in the intensity value, and this jump can be represented graphically like this. You can see this is a one-dimensional image we are talking about. The jump. Jump level means how it is changing frequently or sharply at what point, right? So this is the edge. Edge can be represented by this jump in the intensity value. You can see this, right? Now, The jump in the intensity value can be observed more carefully by calculating the first derivative. The graph below representing this first derivative as the maximum value. So if we take the first derivative, then if we if you focus on the maximum value, this jump is where actually you will find this value, right? This circle here you can see. The edge detection method works on the principle of identifying pixels in the image with a higher gradient value than its neighbors. Obviously, if you talk about edges, edges has the higher values if we compare the other neighboring values. So same concept is used here. Here in such edge detection methods, what happens that means image with a higher gradient value than its neighbor will be considered, means the pixel with a higher, obviously pixel with a higher gradient value than its neighbor will be considered as the pixel that is contributing towards the formation of an edge. Now let's come to the means our main discussion topic today, that of Sobel operator in OpenCV. Now, first, how we go for that? Two derivatives are calculated. Horizontal derivative of image I is computed by convolving the image I with a kernel Gx. I think that I don't need to discuss again about kernel. We have discussed a lot about kernels in last almost all the lectures. Now here also we are going to image horizontal derivative of the image we compute with the help of convolving the image with a kernel Gx. And this kernel we are taking is a odd size, right? Now kernel Gx is given by, say, this one. Okay. Then Gx is equal to what? This is the kernel we are talking about, and then cos I our input image. Similarly, vertical derivative we have taken. So convolution done by multiplying or means convolving image I with kernel GUI. That's simply saying that multiplication with I, and GUI value is given by this. Okay. So this means kernels, some specific kernels we use for specific purposes. In this case, this particular kernel we are using for finding out the gradients, right? You just need to mug up these things, or you need to memorize this, or you can means form your own kernels, and then will observe. You can observe that what will be the output. See, I'm giving it to you. Please have a hands-on experience on different types of kernels. So for this class, we are using this as kernel. Now, for every point of the image, approximation of the gradient at the point is calculated by using the value of the kernel Gx and Gy. How? Like this. Z is equal to square root of Gx square plus Gy square. Or you can simply say Z is equal to Gx plus Gy. So this is the approximation of gradient at any point. So we are taking the values of Gx and Gy, and thereby we are calculating the gradient as a whole of every point. Well, for means in OpenCV, obviously we have some functions to calculate the Sobel operator. Sobel operator, sometimes also called as Sobel-Feldman operator or Sobel filter, right? So it has the means it is a very means frequently used, or you can see everywhere, means where as detection is concerned, maximum of the papers, research papers, they use this particular Sobel operator to emphasize the edges. First of all, it is a discrete differentiation operator. It is used to determine the approximation of the gradient of an image intensity function. And this Sobel operator is a combination of Gaussian smoothing and differentiation. About Gaussian smoothing, we have discussed in the last class. Now it determines the first, second, third, or mixed image derivatives. To calculate the derivatives, k-size cross k-size separable kernel is used. Okay, I'll show you what means we are talking about here by the k-size. Now, this Sobel operator use T cross T kernels, which are convolved with the original image to calculate the approximation of the derivatives, one for the horizontal sense and other for the particle. Then gradients can be calculated in a specific direction, such as normalized x direction gradient, which shows up the vertical edges, or the normalized y direction gradient, which shows us the horizontal edges using this Sobel operator. Now, normalized gradient magnitude from the Sobel-Feldman operator shows us both the vertical and horizontal edges. So we know that gradients are a change in color or intensity. In summary, we can say like that. So change has to do with the derivatives. We are calculating the rate of change, and the kernels can calculate the approximation of those changes. Now, if we talk about the syntax of this Sobel operator in OpenCV, this is the syntax: cv2.sobel. Sobel is the function we are talking about. Now, src, dst, dd, depth, dx, dy, k size. So src, source image; dst, output image; dd, depth of the output image, means size we want to specify; dx, order of the derivatives x; dy, order of derivative y; and k size is the size of the kernel. So theoretical and conceptual part is over. You got it, everything about image gradient, image edge, Sobel operator. Now you have seen the syntax. Let's come to the implementation part of this Sobel operator in OpenCV using Python. See the particular program. You can take a screenshot of this. Import CV to SCV from matplotlib. Import pyplot as well, because I am going to show you the means plots also, but also I'm going to show you the original means image in a different window also, right? Image cv imread, where the exact image is located. I'm taking the Lina image. Now Laplacian, yes, Sobel operator I have discussed. Then obviously one more operator we have, Laplacian. So Laplacian function will give you this particular Laplacian operator implementation part. So image, original image, cv.cv64f, right? Now, this obviously this size we are talking about, that in what size you want. Then Sobel x cv Sobel image cv.cv64f10 k size 5. So size of the kernel we are specifying as the 5. Similarly, Sobel y cv64f, but we want in the means vertical direction, so we are specified 0, 1 k size 5. Then subplot this. So original image gray version, we are showing this as this, and then x tick, y ticks, then subplot Laplacian values, means output. Then this x plot means this Sobel x, then Sobel y. Now this will be the output in the plot. Let me show you first this part. Okay. See, this is the original image. This is the Laplacian, Sobel x, Sobel y. Clearly, you can see in the Sobel x, edges are detected. Sobel y also means horizontal direction and the vertical direction and the Laplacian. Now, I know that you, means the output is not clearly visible here, although because we want a maximum size, we want to have the output in a means visible size, right? So for that, I'm going to run this lines of code in show version. Okay. So let's show you that this is the original Lina image. Now you can see the difference. This is the Sobel x, means x direction, horizontal direction, and this is the y direction, right? Now means vertical direction, and this is the Laplacian operator. Now you can see, if you clearly say one image at a time, let me show you the X version. Okay. So if you see that the edges are properly detected here also, and if you see the Laplacian output there also, you can see the edges properly, right? Yes, with a minor modification, we can have a better output from these two operators, Sobel and Laplacian. And that part I'm leaving it to you. I have also done some research on this particular area, multiple means directional Sobel operator. I will give you the link of that research paper. You can go through it and you can try your own one. So the main code I'm showing it to you. This is the main code. You take a screenshot and perform some modification, and thereby you will get different outputs or maybe a better output. So guys, I hope today's discussion, we have included everything about image gradients, edge detection using Sobel operator and Laplacian operator. In the next class, I'll continue with the edge detection part with a different implementation. Right. So thank you. Bye-bye. Take care.